continental drift idea through 1930s and 1940s. The waning support for Wegener's theory during 1930s and 1940s, as well as few key figures who kept the idea alive. The broader earth science community dismissed Wegener's longitude-based evidence, considering it's unconvincing. Only a small group of dedicated researchers, primarily from the southern hemisphere, continued to support continental drift. Alex de Toth, a South African geologist, stood out as a major proponent. He responded to the criticism of Wegener's work by designing 17 geological tests on exposed rock formation to demonstrate pre-drift connections between the continents. In the northern hemisphere, Arthur Holmes was a rare supporter. He made a critical advancement by proposing that mantle convection would be the driving force behind continental movement, a concept that became central to the later theory of plate tectonics. Paleomagnetic studies. During the late 1940s and 1950s, the study of rock magnetism, initially viewed as a scientific curiosity, evolved into a serious branch of geophysics with a major geological implication. Rocks often exhibit weak natural magnetism, which records the direction and the strength of the Earth's magnetic field at the time of their formation. This gave rise to paleomagnetism, the study of Earth's ancient magnetic field using measurements from rocks and ocean sediments. Paleomagnetic research became critical in supporting theories of continental drift and later plate tectonics by providing quantitative evidence for past movements of continents and reversal in the Earth's magnetic polarity. The magnetic properties of minerals in rocks, focusing on how they relate to paleomagnetism. Most rock forming minerals exhibit paramagnetic or diamagnetic behavior, meaning they can be weakly magnetized. The notable exception is magnetite, which shows ferrimagnetic behavior, a form of strong magnetism similar to ferramagnetism. Magnetite can retain its magnetization even after external magnetic field is gone, making it crucial for recording Earth's past magnetic field. When heated above its Curie point, magnetite loses its ferrimagnetic properties and becomes paramagnetic. Most rock acts as a weak magnet because they contain small, well-dispersed amounts of magnetite, but even this is enough to preserve magnetic signature from the time they are formed. How different types of rocks recorded the Earth's magnetic field through various forms of remnant magnetization, which is a key to paleomagnetic studies. Igneous rocks acquire thermoremnant magnetization as they cool from molten magma. When the temperature drops below 580 degrees Celsius, the Curie point of magnetite, the magnetic minerals lock in the direction of the prevailing magnetic field. The sedimentary rocks acquire depositional remnant magnetization. As magnetite grains settle in water, they align with the Earth's magnetic field at the time of deposition. Metamorphic rocks also acquire TRM, but it reflects the magnetic field during the last cooling below the Curie point, typically after heating from metamorphism. These processes allow rocks to serve as a natural magnetic recorders, helping scientists to trace the movements of the continents and reversals of Earth's magnetic field. Paleomagnetic measurements help reconstruct the past orientation of Earth's magnetic field and introduces the key assumption known as axial dipole hypothesis. By measuring the remnant magnetization in rocks, scientists can infer the direction of Earth's magnetic field at the time of rock formation. Due to current techniques, these measurements represent averages over 10,000 years. Since the time of William Gilbert, 17th century, it's been known that Earth's magnetic field is essentially dipolar, like a bar of a magnet with a north pole and south pole. Today, the geomagnetic dipole axis is tilted about 11 degrees from the Earth's rotational axis, and it changes slowly over time, secular variation. However, Over long periods, these variations average out. Hence, in paleomagnetism, it is assumed that average geomagnetic dipole aligns with the rotation axis. This is the axial dipole hypothesis, a foundational principle in interpreting the paleomagnetic data. The moving seafloor. A major turning point in the development of modern plate tectonics by introducing Harry Hess' 1958 hypothesis of seafloor spreading. Earlier, discussions of continental drift relied mainly on the evidences from land, fossils, rocks, paleoclimate. Seafloor exploration progressed slowly through the 19th and early 20th centuries, but accelerated rapidly after World War II, thanks to technological advances like sonar. In 1958, Hess proposed that the sea floor itself moves, acting as a conveyor belt that carries continents along with it. This elegantly explained a key flaw in the Wegener's theory: why drifting continents didn't leave scars on the ocean floor. Hess' theory became known as seafloor spreading hypothesis, initially dubbed geopoetry due to its bold, imaginative nature, but it would soon be strongly supported by geophysical data. Summary. The dramatic shift in the scientific acceptance of continental drift likening is journey to a fairy tale transformation. In 1912, Wegener proposed was largely dismissed. Continental drift was like Cinderella, unrecognized and scorned by its scientific community, the sepsis. Legrand, an historian of science, saw the eventual acceptance of the theory as almost mythic in nature. The geophysicists of the 1950s and 60s acted as Cinderella's fairy godmother, using paleomagnetism, the magnetic wand, to reveal the theory's scientific beauty. The seafloor spreading hypothesis and the plate tectonic theory were the prince recognizing, validating and uniting with the continental drift to the form of a revolutionary new framework in earth science. Scientific theories evolve, even those as foundation as continental drift. Throughout history, mainly once accepted, ideas have been revised or replaced as a new evidence emerged. So, while continental drift has been broadly validated, especially through modern GPS measurements, which directly confirms that continents move a few centimeters per year, theory is not immune to future refinements. The author resists the fairy tale ending of happily ever after, suggesting that science remains open-ended, driven by continual observation and reinterpretation. Still, as of now, continental drift within a broad framework of plate tectonics offer a coherent explanation that aligns with a wide range of geological, geophysical and paleontological data.